My name is Engineer Steven, and this is the exclusive tutorial. So, my last class I taught capacitance. So, we thought of capacitance, the two equal metal plates made of positive and negative charge. Yeah. But today we'll be talking about the dielectride, the substance found in between a metallic plate. This substance, they are found in between the spacing of a capacitor. They are found at this point. Yeah. They are usually non-conducting material. That is, they are usually mostly a non-conductor of electricity, like your rubber, your air, your oil, those kind of stuff. But most of the times, this dielectric material, some of them exhibit the quality of allowing charge to pass through them. Most of the time, charges. Then, for the function of a dielectride ensures that the large metallic plate is being placed at a small distance between each other. The dielectride ensures that there is a spacing that is being induced between the two metallic plates of a capacitor. That is what the dielectride ensures. That is the first function of the dielectride. A dielectride also increases the capacitance value. Of a capacitor. Then a dielectride also affects the voltage, the potential difference of a system. It could either affect it positively or negatively, depending. It could either affect it positively or negatively, depending on the kind of dielectric material we are dealing with. Some dielectric material can reduce the voltage, some can increase it, depending on the material we are talking of. So, in dielectric substance, remember from our initial formula of capacitance that our C is equal to our E naught A all over D. In the presence of a dielectride, this formula is written this way: C is equal to K E naught A over D, where our C is equal to K C naught. Our K here, being the dielectric constant, could be equal to our C over C naught. This K increases the capacitor's value, like I said, but reduces the value of our voltage and our electric field intensity. So, since our K here is equal to C over C naught, that is the final, the initial capacitance being this value, and the final capacitance being this value, or the capacitance for space being this, and the capacitance for the material being this. Then our K for electric field is equal to our E naught over the normal E, and our voltage is equal to V naught over normal V. Take note, for a dielectric substance that is made of air or vacuum placed between a capacitor, those kind of substance, their K, their dielectric constant, which is equal to our E over E naught, is equal to 1. That simply tells us that their E is equal to their E naught. Their E is equal to their E naught. That's for some of the these are the functions of the dielectric substance. The way you relate it to the formulas, these are the way you relate it. An increase in capacitance being this value, it increases the capacitance value by K. Yeah. And for these ones, it decreases the capacitance value. Let's assume here E is equal to E naught all over K. yeah, it decreases the capacitance value by K. That's how I got this formula for. So I can make K the subject of the formula, K being E naught all over our E. That's how I got this formula. So it's from the function that you can use it's from the function of the dielectric that we can use in getting these formulas that are here. Let me just write this formula on a single plane so you can get it clearly. Our K is equal to our big E naught over E is also equal to our V naught over V is equal to our C over C naught, and is also equal to our permittivity all over permittivity of free space. This is the value for our K at different instances. Then the next topic is, the next subheading we'll be treating is the induced charge and polarization. Let's assume first of all this is a two metallic plate. This is a two metallic plate, one being positively charged and this one being negatively charged. Electric field flows from here to here. In a normal system, this is just a normal system without, let's assume it's air that is found there. This is just a normal system. But when I place a dielectric, let's just place anything here. Like I said, a dielectric is an insulating substance. It can be anything. It could just be oil, it could be rubber, lactic, anything. Provided it can allow the passage of electric field through it. Passage of electric field through it. So from there, the induced charge is produced as a result of the redistribution of the positive and negative charge between the two terminals of the plate. When in the presence of a dielectric material. Our induced charge, remember, this is our charge density. So our induced charge density is produced as a result of the redistribution of the positive and negative charge between the two terminals of this plate of a capacitor in the presence of a dielectric. The phenomenon or the process by which that redistribution takes place, or the redistribution process that we are dealing with, is referred to as polarization. So in between this plate, our E, our electric field, is equal to our surface density, our surface charge density, the net surface charge density, divided by our permittivity of free space. In the absence of a dielectric material, that is, we are dealing with a plate where air is just found inside. Where there is no dielectric material, this substance is not found there. That time, in that kind of condition, our E is equal to our sigma all over E naught. We all know I got this normal from our Gauss law, where our EA equals to our phi is equal to Q over U naught. So if we make E the subject of the formula, we'll be getting Q all over A E naught. And remember that our surface density or surface charge density is equal to our Q over A. Just like our linear density, our lambda is equal to Q over L, and our volume density is equal to our Q over the volume. So after getting this, I'll be moving to the derivation of the formula for the induced charge density. How I will get my induced charge density. Remember, from one of those formulas I dropped at the top of the board, that first at my initial explanation, I said that our K is equal to our big E naught all over our E. This is equal to E, this is equal to E. We know already. So I can remember when for this part here, this our E naught, when this is when it has to do with the electric field, when it has to do with space. That is when there is no dielectric substance present between the plate. It's called our E naught, not E. I made a mistake there. So if we are trying to get our E from here, I can say our KE is equal to our E naught. So fixing that into this formula here, we therefore have that our KE is equal to our sigma over our E naught. Remember, this value was our E. Let's make E the subject of the formula here. If I make E the subject of the formula, we'll be having E is equal to sigma all over E naught K. This E is equal to this E, so I can make them equal to each other. These are two equations. So if I make this E equal to this E from here, I'll be having our sigma over U naught K is equal to our sigma net all over our U naught. We'll be having our sigma all over U naught. So this is the permittivity of free space, this is permittivity of free space. So I believe both of them can cancel each other. Place in mind that our sigma net is equal to our normal sigma as our surface charge density minus the induced surface charge density. That is our our sigma I. So if I place that into this equation, we'll be having our sigma all over K is equal to sigma minus sigma I all over 1. Definitely, if I cross multiply, we'll be having sigma minus sigma is equal to rather K sigma minus sigma I. Rather, we are cross multiplying, so it will affect everything here. So if we are to divide everything by K, I come here, I divide here by K, I divide here by K, and I divide here by K. We'll be having our sigma over K is equal to our sigma minus our sigma I. So since from the question we're told to derive the formula for our induced charge density, I can say from here that our induced charge density, our sigma I, taking to this part of the equation, taking this guy here, we'll be having sigma minus, taking this guy to this part, if this guy goes to the other part of the equation, it will turn negative. I think this secondary work, so it's very easy for you, so you might have understand it by now. So if we take this guy to the other part of the equation, it will now be minus sigma all over K. So this sigma I can factorize, so I'll be having that our sigma I is equal to our sigma bracket 1 minus 1 over K as the formula for our induced charge density. Take note, in the presence of a large density, a large value of our dielectric constant, our K, you will find out that if this as our K approaches infinity, that our sigma I will be equal to our normal sigma. That is to say, the surface charge, the induced surface charge density is equal to our normal surface charge density at that point in time. So that is that for the theoretical part for our dielectric constant. I'll be moving to the calculation part, the other part of my video. Thank you.